Hello everyone, how's it going? My name is Dan the Tutor. Today we're going to be covering AP Calculus AB/Calculus 1, Week 7, the first derivative test. This is probably my favorite lesson out of the 8-week course because we are going to see how we can use derivatives to really, for real world applications. Now, I will say this, in terms of what's the hardest thing in all of calculus, we're actually not going to be covering it this summer. It's called optimization. Optimization problems are basically like you have a field and you can build any shape of a field you want. Let me just show you. You can build a field that looks like this, it's not a field, it's like a fence around a field. So you can build like a square, you can build like a rectangle, you can build like a triangle, you can build like a circle. And basically what you do is you actually find the dimensions that build the fence for the cheapest cost. And the reason why it's the hardest question is because whenever you mix word problems with math, it's going to be harder. And I don't know if you've noticed, but we have really not seen any word problems this summer. That's because derivatives are so hard, you usually don't need word problems to make it even harder. The thing is, when you do add word problems, it's like the hardest thing in calculus. And I think you guys are going to be fine with it because, again, you're already so far ahead than, I guess, your classmates who have never seen this before. But basically, the stuff we're doing today is the introduction to the hardest lesson in calculus. Like, for instance, if this course instead of 8 weeks was 10 weeks, we would probably cover optimization. We're not going to, so that's nice. But if you're really curious, if you want to see what that would look like, I do have an online calculus course you can check out. It's literally free. I don't know why I call it a course because I'm going to charge for money eventually. But for right now, it's free. And basically, you can see problems on everything we've seen this summer, plus I think it's like a total of 44 lessons, something around there, across all the different topics you can learn in calculus. You can find that on my website, www.danthetutor.com. But that's not what's important today. What's important today is that we talk about the first derivative test, which is just a way of finding extrema. So the first thing we need to do is talk about the terms. We have to list out the terms. So first, I want to talk about increasing and decreasing. I'm not going to read off this paper. I'm just going to basically highlight the important stuff. Increasing and decreasing, we're talking about the slope. Obviously, increasing is a positive slope, decreasing is a negative slope. If you have a zero slope, then you're neither decreasing or increasing. We're not going to be looking at zero slope today, though. Not really. Next is extrema. Extrema is just a fancy word that means a maximum / a minimum. So in other words, whenever I talk about extrema, and I use the word extrema today, it just means a maximum or a minimum. But that's the cool thing. That's what we're going to be finding today. And not just across, linear functions or parabolas, which you probably already know how to do for parabolas. It's about the vertex. But you're going to be able to find the maximum and minimum for any function that you know the derivative for, which is why derivatives are so important. Okay, next we have these two terms called absolute extrema and local extrema. Local extrema also has another word, relative extrema. I'll explain that later. But absolute extrema, this is the absolute maximum and minimum value over an interval. And when I say over an interval, I'm saying, for instance, from -5 to +5, or -100 to +52. It's just over some range of x values. Then for local extrema, which I'm also going to call relative extrema, then what we say is it's over not just any interval, it's from -infinity to +infinity. And you actually solve it in two different ways. These problems, we're going to be talking about it in today's lesson, so don't worry about that. And now just as a quick example, I give this, little cubic function right here. How do I know it's cubic? Because I said so, and because I made it. But it's cubic. Anyways, what I would say is that you've got two local extrema, a maximum right here and a minimum right here. Obviously, you can tell that just by looking at the graph because that's where the peak of a hill is and then the bottom of a valley. And then for the other 2 points, you see absolute maximum and minimum. Well, that is talking about this range of values from here on the left all the way to here on the right. That's the absolute maximum and absolute minimum. Of course, you can change those bounds. Let's just say hypothetically, I change the bounds from here to here. Well, now this is your absolute maximum, and this is your absolute minimum, because it's the highest and the lowest point, no matter what. Also, increasing and decreasing is very easy. In green is where the function is increasing. It's going up. Then in the next section of the graph, you're going down. And then in the section after that, you're going up again. Which then begs the question, what's going on in between the green and the red? In other words, at the blue circles I have. The slope's not positive or negative. That is where the slope equals 0. I know I said we're not going to talk much about the slope equaling 0. I want to clarify. I'm going to say that I don't have like an entire range of values where it's 0. So in other words, I'm saying we're not going to have a graph that looks like this today, like just a horizontal line. That's too boring for us. We're not going to deal with that. But what I am saying is you absolutely can have 0 slopes in between, like anywhere. And it just so happens that where the slope is 0, that is the most important points in derivatives. And we'll see why in today's lesson. So, first we need to talk about how to use the first derivative test. Remember, the first derivative test, it's a way to find extrema. The reason why we use the 3-step process we're going to be talking about today is specifically to find maximums and minimums. Step 1, something you already know how to do, calculate the first derivative. So in other words, first derivative, can someone tell me what the derivative of x cubed minus 3x will be?
3x squared minus 3.
Exactly. And that's just a series of power rules. Hopefully you know how to do this by now. If not, seriously, you have to rewatch that lesson. It was like lesson 3 or something, because it's so important. I'm assuming you have this down already. Next, we're going to find the critical values. Critical values are just where the first derivative equals 0. In other words, f prime of x equals 0, which in this case means 3x squared minus 3 equals 0. And now we have to solve for x. So just to do that quickly, add 3 to both sides. So 3x squared equals 3. Then we'll divide by 3. And so you'll get x squared equals 1. Take the square root of both sides. Remember, when you take the square root, it's plus or minus. So x equals plus or minus 1. These are called our critical values. There's also another name you can call them. You can call them critical points. I like to call them critical points personally. I've changed my tune since I made this, I don't know how many years ago, 3 years ago. But basically, critical points are where the slope, in other words, the derivative, because the derivative means slope, it's where the slope equals 0. So that's what I have here. X equals plus or minus 1. That means the slope is 0 at positive 1 and negative 1. And why is it so important that the slope is 0? Well, because that is where the maximums and minimums are going to occur. Now, there is one more thing I do want to say. There's actually another definition of critical points. F prime of x equals 0 is one of them. The other is f prime of x is undefined. In other words, if the function doesn't exist, it's not continuous, there's a 0 in the denominator, any of those cases, you're going to have a critical point as well. Any questions on that point before we go to the last page? Or not the last page, but step 3. Okay. So then step 3, this is the final step for finding at least relative extrema. I'm just going to tell you step 4 and step 5 is for basically other steps. Finding other things in this function. But for the relative extrema, the last thing we do is we're going to do a number line test. Watch this. So first, I make my number line, and then on my number line, I'm going to put my 2 critical points, which were negative 1 and positive 1. Keep in mind, this number line is going to go on forever, from negative infinity to positive infinity. Now, I need to plug in values into my first derivative, which remember was 3x squared minus 3. And I want to see if these values are positive or negative. So let me show you what I'm talking about. Let me pick a number between negative 1 and negative infinity. Like, for instance, negative 2. If I plug in negative 2 in this function, 3 times negative 2 squared minus 3, and you plug this in a calculator or you do the math, negative 2 squared is positive 4, 4 times 3 is 12, 12 minus 3 is 9, and again, if I did that too fast, you can just plug that in a calculator. The fact is that that answer is positive, and that's all I care about. I don't care about the 9, I care that it's positive. So in other words, this entire region is positive. In other words, I plugged in negative 2, I could have plugged in negative 3, negative 4, negative 50, negative 100, negative 1 million. Anything between negative 1 and negative infinity is going to be a positive number. Which then begs the question, well, what's going on at negative 1 exactly? That's 0. And we remember that because we just solved for that on the last page. That's where it's 0. It's 0 at negative 1 and positive 1. Now the next number I'm going to plug in, it's going to be a number between negative 1 and positive 1. You can do a fraction, but I think we'd all agree that 0 is the best choice. So 3 times 0 squared minus 3, that's just going to be negative 3. And again, all I care about is the fact that it's negative, so that's what goes there between negative 1 and positive 1, the negative sign. And then for the last point, I'll pick a number between 1 and infinity. Let's say 2. So 3 times 2 squared minus 3. 2 squared is 4. 4 times 3 is 12. 12 minus 3 is 9. Again, all I care about is the fact that it's positive. So there's my number line. Okay? Positive, negative, positive. And what matters most is the sign changes. Let me explain. You are going to have a relative maximum. You can also call it a local maximum. I don't care. I'm going to call it a relative maximum today, but just know relative max and local max are the exact same thing. We have a relative max whenever you have positive signs followed by negative signs. So for instance, positive to negative, that's what's going on at negative 1. I would say x equals negative 1 is a maximum. I would say x equals negative 1 is a maximum. Technically, I should say relative maximum. I don't have room on this paper, but you can, hopefully. And then if I want to know what a relative minimum is, it's probably going to be the opposite. It's going to be a negative followed by a positive. And that's exactly what's going on at the point 1. To the left of it, it's negative. To the right of it's positive. So for that reason, it's a relative min at positive 1. X equals 1 is a minimum. Now, if you don't have a sign change, for instance, if let's say this is my number line, and I just make up numbers, negative 5, positive 5, and I have this, right? There is no sign change at negative 5. It's not a maximum or a minimum. It's nothing. And then in my example, it's positive to negative, so 5 is a maximum. That's how I read the number line test. So I need a sign change in order to be a maximum or a minimum. And in case you're wondering what this looks like on a graph, this negative, positive here, let me show you. Here's a graph. I'm just going to make up a random graph. And here's negative 1 and here's positive 1. From the left, we're saying we have positive slopes. So something that looks like this. And then at negative 1, like we said, the slope is 0. And then from negative 1 to positive 1, we said we have negative slopes, which looks something like this. And then at 1, again, the slope is 0. And then after 1, we have positive slopes again. This, again, corresponds to my number line that I just wrote a minute ago, positive, negative, positive. And as you can clearly see, positive slopes followed by negative slopes is a max. Negative slopes followed by positive slopes is a minimum. Any questions on that? Okay, then great. So that's just relative extrema. There's this other word called absolute extrema. Absolute extrema, in my opinion, is a little bit easier. The first step is still the same. You find your critical points. And then the second step is different. You don't make a number line test for absolute extrema. I repeat, you do not make a number line for absolute extrema. Instead, you look at your critical points and your bounds. You take your critical points, which, remember, we said was x equals negative 1 and positive 1. And then you got to take your bounds, which I said it earlier. I think I said it on the other page. The bounds were, right here, negative 3 to positive 3. And if you missed that, that's okay. It only matters right now, so it doesn't matter that we missed it earlier. The bounds are negative 3 to positive 3. These four numbers I'm going to plug into my original function. I plug both of these into my original function, not the derivative. And that's what I'm going to do. So remember, f of x, the original function, was equal to, I already forget what it was, x cubed minus 3x. X cubed minus 3x. First I'll plug in negative 3. When I plug in negative 3, I already did this earlier, so just trust me here. You get negative 18. When I plug in positive 3, then I'm going to get positive 18. When I plug in negative 1, I'm going to get 2. And when I plug in positive 1, I'm going to get negative 2. So as you can see here, negative 18 is my absolute minimum, and positive 18 is my absolute maximum. But I'm not going to write it like this. I'm going to write it in a nice looking way. Let me explain. I'm going to say there is an absolute maximum, or max, at the coordinate point 3, 18. Why am I writing it like this? Because x is 3 and y is 18. That's why I'm writing it like this. Then using the same logic, I would say there's an absolute minimum at negative 3, negative 18. And that's how I'm going to write my answer. It looks much better than just pointing with arrows. Any questions on that? Okay. And then one more thing we got to talk about. It's increasing versus decreasing. The good news is we've already done all the work we need. Like here's negative 1, here's positive 1. And we said positive, negative, positive. And remember, this was negative infinity and this was positive infinity on the sides. If we want to write our answer in interval notation, which we do, then for increasing is going to be the hard one in this case. You'll see why. The first interval is from negative infinity to negative 1. Notice you get parentheses. We're not including either point. And then we also need to include 1 to infinity. The way you join that is with the union symbol. It's just a capital U. And then I'm going to write 1, infinity. There. That's all the values where the function is increasing. And then for decreasing, it's just the negative sign, which we already did. It's between negative 1 and positive 1. And that's it. So you'll notice relative extrema and increasing, decreasing, those two questions are extremely similar to one another. The only one that's different is absolute extrema. Absolute extrema, again, uses the original function, not the derivative. Any questions? Okay. So one thing I'm just going to say today, we have now 3 problems we're going to look at. And for the 3 problems, we have bounds. The reason why that's important is because in the example I just did, yes, I had a bound and I kind of ignored it for the most part, except for absolute extrema where you cannot ignore it. But I'm just going to tell you for these problems today and on the homework, I'm not ignoring my bounds. And you'll see why that makes a difference. Okay, so you look here, each of these questions, 3 parts. 1, find all local extrema. 2, find all absolute extrema. And 3, find all the intervals where it's increasing and decreasing. I'm going to answer this in kind of the order I choose to. I'm probably not going to go in the order I said here. It does not matter. Here's what I'm going to say. Step 1, find the derivative. This is a piecewise function. I believe we talked about how to find the derivative of a piecewise function last week, I think it was, when we talked about complex derivatives. Anyways, the derivative of negative x is just negative 1, and that's when x is less than 0. And then for the derivative of the bottom, that derivative is negative 4x plus 4, and that's when x is greater than 0. Notice I can't say x is greater than or equal to 0. The reason why is because if you think about it, if you plug in 0 in for x here, you'd get negative 4 times 0 plus 4. That gives you 4. 4 does not equal negative 1. Therefore, we say the derivative does not exist at 0. And so you can't have an equal sign there. Also because the two sides don't match, because it's not continuous for the derivative, another way of saying it, I'm basically saying the function is undefined at x equals 0. And because of that, x equals 0 is a critical point. So I need to remember that when I'm writing my critical points here, okay? I've got one critical point so far, it's at x equals 0. Now I need to find the other critical points, if there are any. How do I do that? I need to set both the top and the bottom equal to 0 and solve. For the top one, negative 1 equals 0. I mean, that's just no solution. Easy. And then negative 4x plus 4 equals 0. This one I'm actually going to solve. Add 4x to both sides. 4 equals 4x. Divide by 4. You get x equals 1. Be very careful with the piecewise function. X equals 1 works because we're in the region where x is greater than 0. If I flipped these bounds for whatever reason, then it would no longer be a critical point. You wouldn't even consider x equals 1 at all. But x equals 1 is another one of my critical points. So now I have two critical points, one at 0, one at 1. If you remember what I do next, now I'm going to make my number line. Notice this number line is not going to go to infinity this time. It's only going to go from -1 to +3 because that's what my bounds are. I'm not going from negative infinity to positive infinity. Maybe you do next year in your class, just not today. Anyways, I also plot my critical points on my number line, which we said were 0 and 1. Does not have to be drawn to scale. I don't care. Okay, this is good. Now, one thing you ought to know is that now I got to plug in values in between, right? Like, for instance, I need to plug in a point into the first derivative, f prime of x, for a number in between -1 and 0. My advice is pick -1/2. Pick -1/2 right there. So in other words, when I think of the first derivative, which I have written right here, -1/2 is less than 0. And when it's less than 0, the answer is always -1. There's no x to plug into. It's always -1. That means for when I plug in -1/2, I get -1. It's negative. I just put the negative sign on my number line. That's it. Now I need to plug in a number between 0 and 1. Let's choose 1/2. And that's going to be the bottom one because 1/2 is greater than 0. So I'm plugging into -4x plus 4. So that means -4 times 1/2 plus 4 equals, it's going to be -2 plus 4. So you get 2. Positive. All I care about is the positive. I don't care about anything else. And then the last point, this is when we can choose a whole number. Let's choose 2. It's going to be -4 times 2 plus 4. It's going to be -8 plus 4. It's going to be -4, negative. So there we go. I've got my number line. And remember, my number line tells me two very important things. Number one, it tells me where I'm increasing and decreasing. For instance, I can say we're increasing from 0 to 1. And then for decreasing, I'm going to write -1 to 0, union 1 to 3. And again, all of those get parentheses, not brackets. Any questions on that part? Okay. Now, if I want to know where my maximums and minimums are, I got to look at the sign changes. You'll notice at 0, it's changing from a negative to positive, and from 1, it's changing from a positive to negative. So in other words, since 0 changes from negative to positive, I'm going to say there's a relative minimum at x equals 0. And then for the opposite reason, I'm going to say there's a relative maximum at x equals 1. And there's two of my answers. I've got increasing and decreasing, and I've got my relative extrema. Any questions so far? Okay. Now all I need to do is find my absolute extrema. Remember, my absolute extrema, that's where I plug in my critical points, which were 0 and 1, and I plug in my bounds, which was -1 to +3, and I plug each of these into my original function f of x, the piecewise function. So for that, I'm going to say first we'll plug in 0. If I plug in 0, I'm looking at the bottom function. The reason why it's the bottom function, I'll just take us back for a second. The reason why it's the bottom function is because that's when x is greater than or equal to 0. So I need to deal with the bottom function for 0. So that's just going to be -2 times 0 squared plus 4 times 0. You just get 0. Next I'll plug in 1. That's going to be -2 times 1 squared plus 4 times 1. I had to be careful there. I can't just assume it's the same function. The reason why it works is because 1, again, is greater than 0 in terms of my piecewise function. That's going to give me +2. Next, I have, let's try -1 next. Remember, -1 is the less than 0 case, so I have to use the function -x. -1 gives me actually +1. And then the very last number I'm going to plug in is 3. And 3 again is greater than 0. So it's going to be -2 times 3 squared plus 4 times 3. 3 squared is 9. 9 times -2 is -18. And then plus 4 times 3 is 12. it looks like I'm going to get an answer of negative 6 there. And looking at my 4 answers, it looks like negative 6 is my minimum. It's the smallest number. And the highest number is 2, so that's my maximum. But remember how I'm going to write the answer. I'm going to write it nicely. I'm going to say there's an absolute max at the point 1, 2, because x is 1 right here, and y is 2 right there. And then I'm going to say there's an absolute minimum at 3, negative 6, because that's the coordinates for my minimum. And there we go. That's it for that one. Honestly, that's the hardest question of today because it was a piecewise function. The next two will be easier. Any questions on that one? Okay. For next, we have number 2. Number 2 is sine and cosine. I'll admit, sine and cosine may not be your favorite thing, but I like it. So, again, the first thing, if I want to find extrema or increasing, decreasing, I gotta find the first derivative first. F prime of x. Does anyone know the derivative of sine x?
Cosine x?
Correct, thank you. And then again, I have to set that equal to 0. Now, it's funny because I just spent the last hour doing this with my pre-calc kids because we're going over the unit circle right now and solving trig functions. And so I'll tell you, you'll get the answer, where is it equal to 0? You'll get x equals pi over 2 and 3 pi over 2. And of course, if I say this, I'm forgetting some solutions, aren't I? Because technically, because the unit circle goes on forever, you've also got 5 pi over 2, you've got 7 pi over 2, you even got the negative answers, negative pi over 2, negative 3 pi over 2. And technically, this goes on forever. But since we have bounds, anything that's outside of those bounds, I have to cross out. For instance, 5 pi over 2, that's out of bounds. 7 pi over 2, that's too big as well. Negative pi over 2 is too big, and so is negative 3 pi over 2. It looks like the only solutions are the friendly ones, the ones I said originally, pi over 2 and 3 pi over 2. Now I'm going to make my number line, and again, it's going to be bounded by negative pi over 4 on one side, and on the other side, we're bounded by 2 pi. And then in the middle, I'm going to have pi over 2, and I'm going to have 3 pi over 2. And again, I'm looking at my first derivative, cosine x. I'm plugging in values into the derivative. So can someone please give me a value between negative pi over 4 and pi over 2?
0.
0 is the best choice. I would absolutely agree. So then cosine of 0 is just 1. In other words, it's positive. By the way, if you ever get 0 exactly, like let's say you mess up, you forget it's 1, you get 0, that should be a red flag to you. You should never get 0 in any of the bounds because the only point where it equals 0 should be your pi over 2 and 3 pi over 2. And remember, you're plugging in points around those numbers. When I say around, I mean not those numbers. You plug in points above and below pi over 2 and 3 pi over 2. So you should never get 0. That'd be a red flag. Okay, next, I need a value between pi over 2 and 3 pi over 2. Any suggestions?
Pi?
Yeah, I think pi is the easiest. The cosine of pi is negative 1. That's just negative. And then finally, I need a number between 3 pi over 2 and 2 pi.
7 pi over 4?
Correct. Yeah, there's not a lot of friendly choices here, but 7 pi over 4 works. You could also choose 11 pi over 6, and you could choose 5 pi over 3. And of course, we know this, or at least I do. It's positive root 2 over 2. And why is it positive? Because cosine is positive in quadrant 4. How do I know that? Because all students take calculus. And if you don't know that acronym, then, well, never mind. That's just confusing to you. It doesn't actually mean all students take calculus. It tells you what quadrant, sine, cosine, tangent, and I guess all. It tells us where it's positive. In other words, all is all. Students is sine. Take is tangent. And then calculus is the cosine. So that's how I remember all students take calculus. That's the little trick I use to remember which quadrants are positive and negative. So anyways, we got a negative number for that last one. I'm sorry, I meant positive. We got a positive number for that last one. Here's our number line, and immediately I know where it's increasing and decreasing. Where is it increasing? Someone tell me.
from negative pi over 4 to pi over 2, and then like union 3 pi over 2 to 2 pi.
Correct, and I need to erase some of my work because it's going to be too big for me. But you're exactly right. Union 3 pi over 2 to 2 pi. That's increasing, and then obviously decreasing is just the other region. So pi over 2 to 3 pi over 2. Okay, and there we go. Now, again, looking at my number line, I get another piece of information. Can someone new from the audience tell me where the maximums and minimums are?
The maximum would be at pi over 2. And
the minimum?
at 3 pi over 2.
Thank you. You're exactly right. So, and by the way, are those relative or absolute extrema?
Relative.
Relative is correct. Good. So then we would say relative max at pi over 2. And then we would say relative min at x equals 3 pi over 2. And again, that has to do with the fact that at pi over 2, it's positive to negative signs, and then at 3 pi over 2, it's negative to positive signs. That's exactly right. And then, oh boy, we got a fun one for the absolute extrema, don't we? Because we're going to have to plug in these four numbers, negative pi over 4, pi over 2, 3 pi over 2, and 2 pi, into the original function of the derivative. The original function. So that's x equals negative pi over 4, pi over 2, 3 pi over 2, and 2 pi. And I'm plugging each of these into the original function, which was sine x, not cosine x. So first, the sine of negative pi over 4. I'm just going to do all these. I don't care if you know them or not. If you do, give yourself a pat on the back. Either way, I'm going to say them. Negative pi over 4 is going to be negative root 2 over 2. Then sine of pi over 2 is just positive 1. Sine of 3 pi over 2 is negative 1. And then the sine of 2 pi is 0. So I think it's safe to say that 1's going to be our maximum. But it's actually kind of tricky whether or not negative root 2 over 2 or negative 1 is. Who knows which is the smallest number?
Negative 1.
Negative 1's correct. As a matter of fact, what's the smallest value sine can be?
Negative 1.
Exactly. Sine, remember, sine just always goes up and down and up and down and up and down between a positive 1 at its maximum and a negative 1 at its minimum. And in the middle is just 0. So negative 1 is the smallest value it can be. Negative root 2 over 2 is a decimal. It's like negative 0.71. And obviously you can plug that in a calculator if you are really curious. But now we've got our min and max. I'm going to say an absolute max at pi over 2 comma 1. And then we have an absolute minimum at 3 pi over 2 comma negative 1. And by the way, I can think about why this makes sense. Because if I draw my sine graph from negative pi over 4, which is about here, to 2 pi, and I ask myself, where is it the highest and the lowest? It's definitely highest here. This is pi over 2. And it's definitely lowest here. This is 3 pi over 2. So this makes perfect sense. And it looks like so far the answers we've gotten are working out great. Any questions on number 2? Okay. Only one more to go. In my opinion, this is like the easiest one. It's funny, the questions actually get easier as you go on. It's just a polynomial. When we take this derivative, it's just going to be a series of power rules. It's going to be really easy. So first, the derivative, what's the first derivative going to be?
It's going to be 3x squared minus 2x minus 1.
Yep, and then the 9 goes to 0. Good. Now I got to set this equal to 0. Here's probably the hardest question for this problem. How do I factor this? And that's not even that hard. Go ahead.
It's gonna be 3x squared. No, sorry, 3x plus 1, x minus 1.
That is correct. And remember the way you can check that? You can check your answer by foiling. When you FOIL this out, you get 3x squared minus 3x plus 1x minus 1. That is what we wanted. So yes, that works. That's the correct factor. And remember, if you want to solve now, you got to set this and this equal to 0 separately. So 3x plus 1 equals 0. For that, subtract 1 from both sides and then divide by 3. X is going to be negative 1/3. And then for the other one, x just equals positive 1. So here are my two critical points. That's what's going to go on the number line between negative 2 and positive 4. By the way, this hasn't shown up today, but there's a possibility, there's always the possibility, that your critical points are out of your bounds. And what I mean by that, what if we got a critical point at x equals 5? We would literally say that's like out of bounds and you'd literally cross it out, you'd ignore it. So that never happened today, but it could have. And maybe it will happen on the homework, who knows. So anyways, now once again we've got to plug in numbers into which function again? The first derivative or the original function?
The first derivative.
The first derivative is correct. Now I'm going to put this to a vote because we live in a democracy. Which should I plug into? In other words, should I plug into the original 3x squared minus 2x minus 1? Or do you think I should plug into the factored form 3x plus 1 times x minus 1? Any guesses as to what I'm going to do?
Here's my argument. I think it should be the factored form because we just care about signs. And I don't like the first derivative.
You're exactly right. So basically, it's just a little shortcut. It's going to be easier to plug into the factored form, and here's why. If I want to plug in the first number, which, oh yeah, I have to pick in a number between negative 2 and negative 1/3. Like negative 1 works. I'll plug in negative 1. If I plug in negative 1 here, I mean, it's not terrible, but it's like 3 times negative 1 squared minus 2 times negative 1 minus 1. As you can tell, that's not terrible, but if you got like a really hard value for x, and it's got like, squares and cubes in it potentially, that's going to be really annoying. Compare that to if I plug in negative 1 into the factored form. 3 times negative 1 plus 1 times negative 1 minus 1. And basically, the idea is that this, the first number is negative 2, and the second number is also negative 2, and since it's a negative times a negative, I don't even care that it's positive 4. It's going to be positive because you multiplied a negative by a negative. You get a positive. So positive in this region right here. Next, we need a number between negative 1/3 and positive 1, like for instance 0. That's going to be 3 times 0 plus 1 times 0 minus 1. And so for that, you got a positive times a negative, because positive 1 times negative 1. And of course, you'll get a negative there.
Excuse me, I have a comment about that one.
Go ahead.
If we, usually for 0, when I'm doing that, is it fine that I just look at the regular first derivative? Because the x ones will just cancel and then it'll be negative 1.
Yeah, so 0 is a special case. Basically what you're saying is for 3x squared minus 2x minus 1, all that goes to 0 and you just get negative 1, and that's easier than the factored form. You're exactly right. And luckily, it doesn't matter. Like, obviously doing it my way took, what, half a second longer? So it doesn't matter. So next we need a number between 1 and 4. I'll choose 2. So then 3 times 2 plus 1 times 2 minus 1. That's going to be a positive times a positive. We just get a positive. And there we go. So once again, I can tell us where it's increasing and decreasing. But why do that when basically, I think you got it from here. I want you now, I'm going to give you like a minute. I want you to write out all the increasing and decreasing values. And I want you to tell me the relative extrema. Don't do the absolute extrema yet. We'll do that together. But go ahead, pause the video if you're watching online, and go ahead and fill out what you think is the right answer. And then I'll explain. Okay, I'm going to start explaining it. If you didn't finish, that's okay. If you're watching the recording, unpause the video. So here's what I'm going to say. First, for increasing and decreasing, this is the easiest one in my opinion. Increasing from negative 2 to negative 1/3, union 1 to 4, because that's where it's positive. And then for decreasing, we've got in the middle we've got negative 1/3, comma 1. And there we go. There's increasing, decreasing. Now, if I want to find my relative extrema, that is just going to be looking at the sign changes. And of course, the sign changes, we've got positive to negative there and negative to positive there. In other words, we've got a relative max at x equals negative 1/3, and we've got a relative min at x equals 1. Okay, we got our relative extrema, we got our increasing, decreasing. Only one thing left to do, it's the absolute extrema. And as we already know, we're going to plug it into the original function. But can someone tell me what values I'm plugging into the original function?
We're plugging in the critical values and the bounds.
Exactly. So the four numbers from my number line.
Yeah.
So then we got f of negative 2. Why am I in blue? Hold on. Can't do blue. It's blasphemy. F of negative 2, f of negative 1/3, f of 1, and f of 4. And again, it's the original function, x cubed minus x squared minus x plus 9. And I plugged in all these calculators. I plugged in all these values in a calculator earlier today, although you probably don't need a calculator. But for negative 2, I got negative 1. For negative 1/3, I got 9.19. For 1, I got 8. And then for 4, I got positive 53. So as you can see, because of the cube, it's going to explode for really big values of x. So anyways, we can clearly see here, there's my minimum. There's my maximum. And then, of course, I'm going to write it all fancy like I've got an absolute max at 4, 53. And then we've got an absolute min at negative 2, negative 1. And there we go. That's it for today. By the way, with all this relative extrema stuff and absolute extrema, basically, there's even more, obviously there's harder problems than what we've seen today. For instance, what would you say for a problem like this? And we're not going to solve this, but you can just think about it. This is the function 1 over x. The function 1 over x is a vertical and a horizontal asymptote at 0. What would you say for the relative extrema there? It's not so obvious because there's a hole in the graph here. Not even a hole in the graph, there's an asymptote. So we're not going to answer that question today. I just want you to think about it, because basically the whole point of calculus and math, especially math at a college level, it's a lot less reverberating what you were taught in school. A lot of it is actually thinking about the solutions on your own and what would happen. Because let's be honest, when you're in college, a lot of the learning is on your own. And you're either going to find that out the easy way or the hard way. And the easy way is me telling you now. A lot of the work is going to be done on your own. The hard way is you're waiting to hear your professor tell you the answer, and then the test shows up and you haven't covered like half the stuff. Because a lot of the learning is supposed to be on your own. You know, there's going to be a lot of textbook reading. Believe me, I don't like reading textbooks in math either. But that's basically what they kind of force you to do. So that's enough scaring you about college for one day. You'll get the full experience one day, I'm sure. So thank you all for watching tonight. Please do the homework. And I'll see you next week for the final lesson, week 8. So see you guys later, and bye-bye.